All right. You know what today is? It is our last in-class lecture for Engineering 213. The homeworks are being graded, but I actually saw my TA right before this, and I think they're all graded, all the homeworks. I just didn't get a chance to turn on the grade columns because my TA, she told me at like 12:45 or 12:40. I was like, well, I'll do that, but I gotta go. So I think they're all graded. All the homeworks are graded. All the solutions to all the homeworks are now posted. If you go to Teams, you will see that all three exams, their problems and the answers have been posted. Did everybody see that? Okay, good. The attendance grade after today will be up to date. A student informed me a little bit ago that I guess somebody went onto the spreadsheet on the at-home game and made some changes, like inadvertently. It wasn't. I don't think it was a mistake, but the grade wasn't matching because somebody went in and changed some stuff. So I'm going to post a new at-home game. If you want to mess with it, download your own copy. Don't edit the copy that's on Teams. But I will repost that. Okay, everybody okay with that and clear? Okay, all right. Now, I have another housekeeping item, and then I think I need to poll the class because I have a question for you. But first off, the course eval, most of you have done it, and if you go to your homework grade on Blackboard, you will see that for the vast majority of you, I've already given you your 10 bonus points if you've done it. If you have not done it, you're leaving points on the table. So again, you can say I'm the worst professor ever, but please do it. If you have any genuine, honest suggestions about what to do for future offerings, let me know. I really, would appreciate it. Like I said, I've never had a class this big before, so I definitely would appreciate any feedback that you have. And if you upload a proof of completion, you get 10 free points. So right before or earlier today, I checked Blackboard, and 43 of you had done the upload. But on MyMU, I can see how many of you have done it, but I don't know which ones have done it. I saw that 45 had done it. So 2 of you have done it and didn't upload the proof. So if you haven't done that, again, it's free points. Now, before we get into Q&A on the final, I do have a question for you. I got a question posed by a student on Teams. It's actually a pretty reasonable point. Every now and then, I'd say for a couple of you, we've had some issues where a laptop has died during the exams, and we've had 1-hour exams, and we're about to have a 2-hour exam. And so there might be a bigger epidemic of battery failures during the exam. It might make a little bit more work for me, but I'll go ahead and pose the question. Would you prefer a paper-based exam for the final?
Could we still use our laptops like
Yes, that's fine. I have no problem with you using your laptops I have no problem with you using your laptops for accessing the notes or anything like that. But in order to administer the exam, would you prefer me to just have a paper-based exam? Would that be easier for the class? Okay. Anybody opposed to that? Because one thing, I am going to have like 8 conceptual questions, and it'll probably take a little bit longer to write those out. But again, as I said with the conceptual questions, I don't need the Shakespearean sonnet. I only need a sentence or two. Is that okay? Yes.
Could we just have it in the engineering building with the fancy tables?
I don't know right now. I got the question about maybe an hour or so before class, and I'd have to go through and assess the schedule because I got to find a room for 60 people, you know what I mean, during finals week. So I don't know. That's my point.
Is it a possibility, though? Good?
It's a possibility, but
You're the boss.
No, I'm not. Listen. When I first got named associate dean, half of the people that found out congratulated me. The other half offered their condolences. The facts are that is So far from the truth. But in all seriousness, so like the most ideal candidate would be like 1201, 1203, 1205. But for one, there's classes probably in there right now, and if there are classes in those rooms right now, then they have the same final exam slot that we do, you know. So that makes it a little tough. But if I do a paper-based exam, it might make it a little bit more difficult for me to grade, but it fixes the laptop problem. It does, you know. I could try and craft some of the conceptual problems so maybe they're a little bit shorter, so it doesn't add too much work on that end. Like I'm not going to ask you some super, you know, vague. I've never been one to ask super vague conceptual questions, and so I'm not going to start doing that now. Again, probably makes it a little harder for me to grade. I can try and look, but I'm not optimistic. Is my point. So because I'd have to have pretty much all three rooms to be available, and I'm not sure that they are. So I'll let you know if they are optimistic, or I'll tell you what, if they are available, I'll put it to a vote, and if they're not, I'll call the ball. We'll do it paper-based. Does that sound good? Okay. All right. What's that?
You can run extension cords.
Yeah, we'll get 60 extension cords, and then we'll start the exam, and we'll hear the fire alarm go off. Although this time it'll be real, you know.
I mean, that seems like a good way to get it over with.
That seems like a good way to find myself on WSAZ News, you know. What's that?
Cabell Midland did it like 3 or 4 times within a couple of months. Yeah, you know, it's like all the junior year.
So you're really making me look forward. Like my daughter's 3 years old, so she's certainly not old enough yet. But we live in Malcolm Springs, so I can tell you she'd go to Cabell Midland, you know. So.
Everything you hear is good. Yeah.
Wayne County.
I lived in Wayne County, I lived in Midland, so.
Cabell Midland? What?
Yeah, I lived in Cerrito, so.
I lived in Cabot.
Yeah, he's done.
All right, back to Engineering 213. All right, so that's the game plan. If we end up doing a paper-based exam, I will send an email to everybody in the class. Again, I don't like changing plans. I think that one of the most beneficial things I can do for you as an instructor is stick to the plan, but it was a very good point. And if I have 60 students whose laptop dies all at once, that's going to make for a very difficult exam to grade. And so I'd rather make sure that it's fair and equitable for everybody in the room. So I will keep you posted. All right. I'm not going to go through the advice and stuff that I went through last time because I've already went through it. The whole point of today was to collect as a whole. You've had some time to chew on the last 3 exams. I know I posted them this morning, but you've got the exams. You know, you took stock of what I said on Wednesday. The floor is yours for questions between now and the end of class. So, floor is yours. Any questions for the final? Exam 1, material 2, 3. I didn't get any posts on Teams, or did I? I don't think I saw anybody post any questions they'd like me to do or anything they'd like to answer. Yes, sir.
Could you go over an example when, like, the shear moment diagram for the shear would be linear and the moment diagram would be parabolic?
Sure. The easiest, so the one thing I can tell you is that if you're having trouble identifying when a moment diagram would be parabolic and when it wouldn't, that's an easy thing to remedy, okay? So let me show you. Let's go to Engineering 213. Right here. It's a perfect example, okay? So this was the second shear moment diagram example that we did as a class. So the question was, when is a moment diagram like parabolic and when it's not? Here's the beam, okay? Now this beam, I'm going to reference points A, B, C, and D. The moment diagram will be parabolic between points A and C, and it will be linear between points C and D. And how did I identify that? It's where the distributed load is, okay? The distributed load is a constant load. The integral of that is a line. The integral of that is a parabola. So the moment diagram will be parabolic between A and C. Between C and D, there is no load. No load means constant shear. Constant shear means linear moment. And so when you scroll down and look at the moment diagram, you'll see that's exactly what we found. Parabolic moment diagrams between A and C, linear between C and D. Let me scroll that up just a little bit so that we can kind of see the shear diagram in there too. Did that make sense? Yeah. Okay. Since we're on the topic of shear and moment diagrams, are there any other questions about shear and moment diagrams? I think that as a whole on exam 3, the class did pretty well on this topic. I think the main issue on this problem on the exam, well, there were a couple. For one, like I said, if you did not get the correct support reactions for problem 7 or problem 6 on the last exam, if you missed the support reactions for those two problems, I would study that. I would spend a fair amount of time, I would invest time in making sure that you understand how to compute those support reactions because they affect a great many topics in this course, and understanding them will clarify future or additional topics like centroids. The x and y distances when computing the location of a centroid are just moment arms. And if you understand that, I think it will clarify things down the line. So that was one mistake. The other mistake I think that was most prevalent on the exam, the last exam, was just not finishing the problem. A lot of you, what you did is you looked at so this is a perfect example, okay? So let's take a look at just the shear diagram, okay? So there was a few of you that what you did is you looked at the shear diagram and you said, okay, I integrate the shear diagram in order to determine the moment diagram, and I see that the maximum number here is 1400. So that's the max moment. That's not correct, okay? If you actually carry through the construction of the moment diagram, you will find that the maximum moment is either 1066 or 1200, not 1400, because it's all about how those areas are distributed from beginning to end. And so there was a few of you just looked at the shear diagram and went, oh, the beam's going to fail. And no, it didn't, because if you actually carry through the construction of the moment diagram, you found that that beam was fine, okay? So don't skip steps that was kind of one of the pieces of advice that I was discussing during the review last time, and that's sort of what I was referring to. So, does that make sense? I'm sure you've got more. Don't hesitate. Don't be shy. This is your last chance to do this in person. So please, if you got any further questions, ask them.
Do you know if there's going to be anything to do with trusses on the exam?
Possibly. Yeah.
Do you think you could give a little refresher on moment of sections or method of sections?
Method of sections. I could, yeah. Let's see. So I think that with the method of sections, I would so first off, again, and I don't mean to sound like a broken record, but with both truss analysis, this is method of joints and method of sections, and the construction of shear and moment diagrams, if you don't get the support reactions correct, you're going to have problems, just point blank. So again, not to sound like a broken record, but if you missed the support reactions on problems 6 and 7 on the last exam, study that, okay? All right. Now, I would argue that the toughest thing about the method of sections is the art, if you will, drawing out the schematic. I mean, what literally might be the easiest thing to do, and I have done this before even when I was a student, is I would just start drawing the truss and literally take my eraser and just start erasing it on the other side of the section, right? Because if you look here on the top, so see that little Z highlight in yellow? Those are the 3 members that we were trying to investigate for this example. And you notice this is my schematic, and I literally just drew the truss up until this point, okay? And again, this is another one of those things where if you try and skip steps, if you don't draw it out, if you don't draw it out neatly, okay, this is where you can start to mix up slope ratios. This is where you can start to forget loads. Take the time to draw it out, okay? Take the time to draw it out neatly. Bring a straight edge, okay? Everybody in this room has a straight edge. Boom. Straight edge, you know. ID, driver's license, debit card, boom. You have a straight edge. Everybody in this room has one, okay? Use it, okay? Make sure that when you're constructing the section that you don't forget any loads, right? Let me scroll up just a little bit, okay? So I'm constructing a section here by cutting a section and looking to the left. By cutting a section and looking to the left, I have the 16 kip and 23 kip reaction at B, which I have located here, and the 28 kip load at C, which I've located here. Don't forget anything. This is a clear case of where you can make a mistake. If you forget to put a load there, when you start performing your structural analysis, you're going to get the wrong answer if you don't account for all the components. Okay? Does that make sense? So I think that is half of, if not maybe even more of the battle than the actual math. Now, in terms of the strategy of doing the problem, okay, so first off, whenever you're looking at, so for this particular section, what I do is any of the horizontal and vertical members, I identify those members in tension. I identify all the members in tension, but for any of the diagonals, I identify their X and Y components, okay? And then I strategize, okay? For this particular problem, there are 1, 2, 3 horizontal components, 1 vertical. So I can sum verticals, sum forces in the Y direction right now. Okay, I got 23 up, 28 down. I need another 5 up so that I have 28 up and 28 down to meet equilibrium. Next thing, whenever you have one component of a diagonal, use the slope ratio trig, however you want to do it, to get the other component. Okay? So now I've got this diagonal figured out. Now I have 2 remaining unknowns, and they're both horizontal. Okay? They're both horizontal, so summing forces in the X direction will not get me anywhere. Okay? All I'm going to know is that this plus this equals 16, but it's not going to tell me what each one of them are. Okay? So the next thing you'll do is sum moments. Where should you sum moments? I propose that you should sum moments wherever a bunch of the unknowns intersect. So a good candidate would be like summing moments at F, maybe summing moments at G, okay? Whenever you sum moments, what you kind of want to think about is isolating a given unknown, okay? So for example, if I sum moments at F, this unknown and this unknown all go through F, so they generate no moment at F, and the only thing I'm going to be left with is this, all right? So now I've got the diagonal figured out, I've got this figured out, then I can sum forces in the X direction to get the last one, okay? Notice how I've been sitting here rattling out talking for a few minutes. I haven't done any math, okay? I highly recommend that, particularly on problems like truss analyses, shear moment diagrams, any of the problems that we have done in this course where there's multiple steps, that you just strategize a little bit. Think a little bit about what you're going to have to do. Part A to part B, part B to part C. What tasks do you need to achieve to move on to the next component of the problem, okay? That's a skill that's going to be valuable to you, not just in this course, but in future courses, okay? That is a skill seminal to the field of engineering, period, okay? And many of your courses moving forward are going to have a structure like that, okay? So everything I just said, did I do that? Let's see if I did that. So what did I say first? I said sum forces in the Y direction. That's exactly what I did first. Then use the slope ratio to get the component in the X direction. Pythagorean theorem, boom. There's the diagonal. Then I said I was needing to sum moments. I said sum moments at F. Well, by golly gosh gee, that's exactly what I did. Sum moments. Now I've got the remaining component. Some forces in the x direction. I have the final unknown. Notice how at the beginning of the problem, I assumed every single member was in tension. By assuming every member was in tension, any member or any variable that came out negative, I knew it was compression. You can do that with method of joints or method of sections. It doesn't matter. Is that good? How about anybody else? Any questions about this? What about some of the earlier stuff? Because we've been talking about trusses and shear and moment diagrams. We got particle statics, the cross product stuff. Don't forget all that. That's going to be on the exam too. Yes?
Would you be able to go over part B of homework 3.3?
Okay. All right. Yes. 3.3 you said? Yes. All right, I'm going to have to remember what we were doing on this problem. Okay, hold on. Remind me. Let me get my textbook here. This is why I brought my textbook. Yeah, they gave me a loose bound textbook here, so give me a second. Okay, so that we're all clear on this problem, okay, let me pull up the, I have a little presentation file that has all of the images from the textbook. Excuse me. Right. Here we go. Here's the problem. Okay, so this is the homework problem that we did on homework 3.3. And so what we have here is a crowbar that is yanking this nail out of a piece of wood. Okay, and so the question was about part B. Okay, so in order to explain that, I think we need to go back to part A. So part A asked, what is the moment about point B that's generated by this force? Okay, now what the problem states is that we have this crowbar trying to yank a nail out of a piece of wood, and we know that it takes 200 pounds, of force to yank this nail out of the piece of wood. So given the scenario, what would that force generate in terms of moment about point B? Well, if I have a 200-pound force going like this, 200 pounds times a moment arm of 4 inches generates a moment of 800 inch-pounds. Is everybody okay with that? Does that make sense? Okay, so it takes 800 inch-pounds of moment about this point right here to rip that nail out of the piece of wood. And so the question was, what's going on with part B? So part B is asking, okay, what is the deal with this force? How much does this force need to be in order to yank that nail out? Well, that force needs to be whatever magic magnitude is necessary in order to generate 800 inch-pounds of moment about point B, because 800 inch-pounds of moment is what's going to rip the nail out. So, with that context in mind, let's look at the problem. Now, moment in this case, this is a two-dimensional problem. So the moment is defined as r cross f. But r cross f in 2 dimensions is just rx fy minus ry fx. So all we need to do is define rx, ry, fx, fy, and then plug and chug. So let's start with the force. The force in this case is this, give me 1 second. So here's the force, right? And we were given at the beginning of the problem that the magnitude of this angle alpha is 10 degrees, okay? So cosine and sine of that angle, the cosine of 10 degrees and the sine of 10 degrees, the x component is positive, the y component is negative because it's pointing to the right and pointing down. So the force is defined like this right here, right? So a x component that's positive, a y component that's negative, but we don't know what the magnitude is, right? So it's cosine of that angle times the magnitude of I, sine of that angle times the magnitude j. That is a definition for F. That's the force, okay? Now the R vector is from the point in question. We are summing moments about point B, from point B to point A, right? What is R? R is a position vector from the point in question about which we're summing moments to the line of action of the force. So a simple way of doing that for this problem is just from B to A, right? We know that this is 18 inches. We know that this is 70 degrees. So 18 cosine 70, 18 sine 70. We get this. So now we have R cross F, right? We have, this is our R vector. The x component is negative. The y component is positive. Notice that for R, there's no variables. We know the distance. It's 18 inches. We know the angle 70 degrees. So it's simple. For the force, we don't know the magnitude, which is why it's a polyjunct times P and a polyjunct times P. So this is Rx, negative 6.1564 inches. This is Ry. This is Fx. This is Fy. Again, that's negative. And so when we evaluate our cross product, the cross product Rx_Fy minus Ry_Fx, this is just evaluating the cofactor expansion in 2D. So we get Rx times Fy minus Ry times Fx. We can factor the P out. So this times this minus this times this, tracking your signs, you get this value here. Take that, set it equal to the moment of 800, and so the force has to be like 50-some pounds. Does that make sense? And so to further clarify the problem, or to go through the problem in completion, the last component of the problem said, okay, what's the minimum amount of force required to yank that nail out? Well, the crowbar is 18 inches long. The minimum force would be completely perpendicular to that crowbar. So if the moment is 800 inch-pounds and the moment arm is just the length of the crowbar, we can yank with a perpendicular distance, and the force is just 800 over 18. So it should make sense that this part C should generate a force that's less than the force generated in part B. Because part B is saying, what's the force required at this angle to yank the nail out? And part C is saying, what's the minimum force required to yank that nail out? So a gut check should be, well, that should be less than that. Does that make sense? That make sense? All right. How about anybody else? Is everybody good on this? Is this clear? This is a good review problem. This is a good one to look at. What do you think? Any other questions about cross products, about moments, equivalent systems, core force couples, anything like that? Yes?
You go over pulleys.
Pulleys. Okay. That's a good one. Do we have which homework do we have on that? Was it 3, 4? I can't remember. Nope. Hold on. Wait, no. This is way back. This is like 2.4, 2.5, something like that. Okay, all right. This was 2.67. Okay. So I will go ahead and just, be blunt. I may have a pulley problem on there, but it's not going to be one that looks like something, that Spider-Man would entangle one of his villains in or whatnot. Spider-Man and Doc Ock got into a fight, and this is what happened. What's the tension in the web? Give me 1 second. Here we go. Perfect. Okay. So I think that the biggest thing to do with pulleys is I think that the fairest way to assess it is one, don't overcomplicate the system, but two, isolate all of the ropes or all of the cables that are associated with the weight in question. So, for example, if I look at option A, okay, option A, what I'm going to be doing is I'm going to be cutting a section with, again, secret weapon, samurai sword, or lightsaber if you're a sci-fi fan, and I'm going to be cutting all of the ropes or cables associated with this mechanism, okay, because this is the mechanism most closely associated with the crate. Whereas for part E, I'm going to be cutting all of these ropes because this is the mechanism. This is the pulley. Now, if I'm looking at, let's say, part A, this is sort of the overall point I want to make. If I'm looking at this mechanism, how many ropes or cables am I going to be cutting through to drop this crate onto my foot? I'm going to be cutting through 2 of them. The same thing is true for option B. To drop this crate on my foot, I've got to cut through 2 of them, okay? So I propose that the tensile force in the cable from scenario A versus the tensile force from the cable in scenario B are identical, okay? Just because I have another pulley up here doesn't affect equilibrium conditions of this system. Does that make sense? Is everybody else okay with that? So if this crate weighed 1,000 pounds, then I propose the tensile force in the cable here is 500. Because, again, cutting through this, I'm cutting through 2 cables. So there's a T force going up, a T force going up, 1,000 pounds going down. That T force has to be 500. Does that make sense? Same thing is true here. Now, if the crate is 1,000 pounds, what is the tensile force in the cable for scenario C? If the crate weighs 1,000 pounds, 333.3333 pounds, right? Because there are essentially three tensile forces sliced through 3 cables to hold this up. What about this? What about that? Same thing, exactly right. Same thing. So if I got rid of this wheel up here and this rope was just out in space, it'd be no different than this scenario over here. No different, okay? This one right here, 1, 2, 3, 4. It'd be 250. Does that make sense? See that? I think this one was the one right here, the scenario D. I don't think we ever actually explicitly looked at this one because I think we had 2 in class, 2 on the homework assignment, but we never looked at scenario D. So, I think. What?
You're talking about the difference between D and E, and I mean because they're essentially the same system, just reversed.
Yeah, that's a fair point. Yeah. Wait, what?
So
Oh, yeah, you're right, yeah.
But at the same time, your
Wait, hold on.
tension in D is going to be different than your tension in E. From a realistic perspective, some of these systems are going to provide less friction than others as well.
That too. What? Listen, I'm going to be completely frank. That's not going to be on the final. What time is it? One question that we aren't talking about, and we do have a little bit of time, nobody's asked any questions about particle statics, and that was like the stuff on the first exam. And, I mean, there's pulleys, yeah, but, I mean, we're talking about the 2x2 system stuff, the 3x3 system stuff. Did anybody have any questions on that? Because I know that was a long time ago, but that could be on the exam. What'd you say?
It sounds like it's going to be on the exam.
Well, let me see if I can identify the homework that I think might be best to review. Now, and I'm not saying, here, let me say this. I'm not saying you're going to get this problem on the exam. There are some homework assignments that I think might be beneficial from a study standpoint. Like homework 3.3 is actually a pretty good one. Let me see, is it this one? Wait, that's the assignment. No. Is it this one? No. Let me try this. I think it might be 2.4. All right, this one I think would be a really good one to study. I'd say probably the second problem more than the first, because the second problem has more loads. I'm not telling you this is going to be on the exam. I'm saying that I think that this problem reviews a lot of like good skills, and it also I think would force you to break out the 2x2 solver in your calculator. We haven't done that in a while, so we haven't done that in a long time. So I think that might be valuable. Beyond asking me if I'm teaching Engineering 214 next semester, because again, the answer is no. No. No.
We wouldn't be upset, I promise.
I can't do anything about that.
Actually, you can teach the class.
No. No, I can't. I'm teaching plenty.
But you're not teaching enough.
What is that supposed to? Yeah, hold on. Yes, sir.
How about you just teach all of our engineering classes from now on? Just like right now, we'll get one teacher and just teach all the subjects.
Okay.
That works. Anybody opposed? We could make collaborate.
We can just stay in the same room all day.
Just hang out with Dr. Mike. You know, that's the degree. Hold on. We're getting a little off topic. Are there any questions at all? I mean, we've kind of been working backwards. We haven't been. I just want to make sure that you're getting your money's worth for your review session. So. Sure. So with this problem, this is a particle static equilibrium problem. So one of the reasons why I think that this problem is so beneficial from a study standpoint is, number one, it's not 3D, and I do not think that three-dimensional problems are any more complicated, but I do think that they are just longer. If you understand the process for 2D, you understand the process for 3D. It's no different. The other reason why I like this problem is because you are forced to add vectors. And you are forced to add vectors in the most efficient manner possible, okay, which is what I like. All right, so this problem has 4 forces that are all intersecting a given particle. So because of that, there are no moments because all the forces all intersect to a common point. And we have 1, 2, 3, 4 forces, but 2 of them are unknown. Okay? In a particle statics problem, if it's 2D, you can have no more than 2 unknowns, and the only way you can handle more than 2 unknowns is to talk about engineering 216, because that's indeterminate, and that's kind of some of the stuff we talk about in there. But in this scenario, we've got 4 forces, and so the very first thing that you should consider that you need to do is to describe those vectors and add them up. So for example, every one of these vectors are all going through a common point, and they're all at a given angle. So for instance, TAC is in the second quadrant, so the x component is negative, the y component is positive, and it's just the magnitude times the cosine, magnitude times the sine, okay? So the very first thing that you should consider doing, or that you should do well, again, as I've said, structure your problem. Step 1, describe the vectors. This is the tensile force in cable AC. This is the tensile force in cable BC. Again, negative, positive because it's in quadrant 2. Positive, positive because it's in quadrant 1. What about the 2 applied loads that you do know? Okay, force F. It is along the x-axis and it's negative, negative 200I. For force P, it is in quadrant 4, positive x component, negative y component. And it's the same format as all the others. The only difference is you know the magnitude. Here's a variable times cosine, variable times sine. Here's a number times cosine, number times sine, because you know the magnitude, okay? So the next thing that you do once you've described each of these vectors is you add them up. And the way that this works is you add up all the components associated with the I vector, and then you add up all the components associated with the J vector. And because this is a problem in static equilibrium, the sum of those components must be 0. So all this first equation is right here is just adding up all the stuff in front of I, right? TAC times the cosine, and it's negative. TBC times the cosine, and it's positive. 200 newtons, and it's negative. 300 cosine 45 degrees, it's positive, okay? Same thing with here. Add up all the components associated with the J vector, okay? That's the hard part. The rest is just algebra and grunt work. So what I'm going to do is I'm going to take this system, I'm going to write it in matrix form, right? So well, how do I do that? I take the TACs, group them together, the TBCs, group them together, and everything else move it to the other side of the equation. So I get, look at what I have here for the TACs. I've got this grid of 1, 2, 3, 4. 1, 2, 3, 4. Lay out that grid. Everything over here, that's the other side. Plug it into my solver, in my Casio or equivalent calculator. Boom. That's it. Now you know the magnitude of the 2 unknown forces to keep the system in equilibrium. And that magnitude was developed based on the understanding that these 2 equations up here had to sum up so that the total amount of force was 0. Does that make sense? All right. Any other questions? Yes? I'm a tough one to shop for. I do have a couple of things I want to say. We are getting short on time. I have a couple of things I want to say to close out the class. First off, again, some housekeeping. I obviously haven't updated the attendance grades today. I will do that. I will update. I will turn on all the grade columns for the homework, and I will fix that at-home game spreadsheet. Again, don't modify the one on Teams. Just download your own copy. A couple of other points, and then we're going to call it for the day. First off, if you haven't done your course eval, do it. Upload the proof, free bonus homework points. I will email you and let you know about the exam probably by the end of the day. Finally, I do have a couple things I want to say to close out the course because I'm the professor and I get to do that. This is, I think, admittedly been a weird couple of years for you. I think that's a fair statement. Many of you are coming into this course from online calculus, online education last year. And even though we're back in person, you've had a weird couple of years. I didn't have to go through this when I was in college. I didn't have to, go to class and wear masks or, watch, professors who didn't know how to operate, live stream, try and teach physics and whatnot. And I'm not speaking about any one person. I just don't know. I just, speak from experience. But one of the things that I think is admirable, and this is the honest truth, is that I, throughout when we went through the initial lockdown to the pandemic back in 2020 up until today, I really haven't heard many engineering students complain. I mean, I know it sucks. I know we're tired of this. I know we want to go back to normal. But I haven't really heard many of you complain. You've knuckled down and gotten the work done. And I know, engineering's not an easy curriculum. It's not, and so you've had a very, tough experience just from the fact that it's engineering, but coupled with the shell shock of having courses online to now having them in person, that's tough. I fully recognize that. And so I just wanted to say as we close this out that I am proud of every single one of you. You have met the challenge, in my opinion. I think you've done very well. And I'm excited, if possible, to have you in courses again, even at 8 o'clock in the morning next semester. So with that, that's all I've got. I will see you all next Friday. That's all I got. Oh.